So here's the closer look. Why is it a closer look? Because we actually can simplify this problem. We can say, okay, why don't we only focus on the x-axis? We only have diffusion in the x direction. Okay, and this is what you can do, and then you end up with this equation, with the top equation. It's only x. And then you can also think about what do you need to have in order to have no more change of the concentration. So no more temporal change of the concentration means the left-hand side is 0, implies that the right-hand side has to be 0. When is the right-hand side 0? It's 0 if the slope of a distribution or the gradient of a concentration is constant, because then you have no curvature. It does not depend in the end on the diffusion coefficient at all. The final state only depends on, well, probably how long it takes, but you get a constant slope. And there's a little image here behind me. So you have an initial distribution, and this one is the x-axis shown here. So you have an initial, this one is the wiggly curve. Okay? And then for this problem, you need boundary value. You need to say what happens at the boundary. And in this example, I just keep the boundary values constant. Red bars here refer to the boundary value. Always stays the same on this side, on that side. And then over time, the final distribution that you get is actually a line connects. And this is what diffusion does. It removes curvature and distributions of a property. Okay, so there is in the oceans, there's diffusion of scalars like temperature and salinity, but there's also diffusion of actually momentum like the flow velocity. And there's also diffusion of what we call momentum. So this is what we call diffusion.